again, YouTube. I have completed the curriculum for Phase 4 at the Flatiron School, and I have completed my Milestone project for Phase 4 at the Flatiron School. If you're new to the channel, you're new to the playlist, I'm Zeth Abney. I am currently a student in the Data Science Boot Camp, the Flatiron School. I've just completed Phase 4, and I'm going to share with you guys today what I did for my Milestone project. After this project, I have now been approved to begin my capstone project, and I will be vlogging about that following this episode. So, this Milestone project required me to source my own data, decide what kind of algorithm or model I would use, what kind of algorithm I would use to model the data that I sourced on my own, which I sourced from Kaggle. Big surprise there. And what else? Yeah, there was probably like the least amount of instructions with this project. They were kind of like, cool, you've done a lot of data science at this point. Do more data science and get back to us. And that's kind of what it did. So I went the computer vision route, and I built a convolutional neural network that essentially views JPEG images of chest x-ray scans, and it classifies them as either showing signs of pneumonia or not. So, interesting thing with Flatiron School, they pretty much always require you to address some sort of like business issue or solve some kind of business problem with your project, which is interesting to me because there's a lot of like things you can really do in data science, a lot of cool things you can build and interesting things to discover, that the business application for it isn't all that obvious or self-evident necessarily. But I get it. Like, it's, you know, you're trying to get a job and to get hired to do stuff, unless you're in academia or something, like you need to create some kind of value like for the business, right? So that was a little bit interesting to like figure out like exactly what the business use case is for this project, but you know, we got the thing done. Yeah, this says blog post URL. It says in progress because this is the blog post to this video right here. So anyway, yeah, the goal of this project is to develop a convolutional neural network designed to view images of chest x-ray scans and classify the images as showing symptoms of pneumonia, a label of 0, or not, a label of 1. Not pneumonia, a label of 1. So yeah, it's binary classification, computer vision, convolutional neural network. Nothing like super groundbreaking necessarily. So the business use case that I decided on was basically, I took the approach of all the previous projects. They were like, you're basically pretending to be working for a company and you're doing this project for them. Talking like through in the markdown, like in the README and everything, talking about, you know, like LLC International or whatever, like just seemed kind of corny to me. So I went the route of like, I'm an independent developer and I am pitching this model to be bought by some business that already provides medical software as a service, or you know, like when you go to the doctor and you get your X-ray, there's some software that they're using to store those images, to read them, to, you know, run the X-ray machine, like all that stuff. So the basic idea or the basic business use case is that this model would be a new feature in the existing software, as opposed to being a whole new application on its own, right? So, you know, if you're the doctor or the X-ray technician or whoever, you would just, you know, one day you'd get a software update and this is like a new option, a new option in whatever drop-down menu you're already familiar with. So yeah, that's basically the business use case. The idea is that it would sort of extend or augment or expedite what the doctors are already doing. It wouldn't necessarily replace the need for humans to kind of check and read the x-rays, but it could cut down on the time that it takes to get through all the different diagnoses that the medical professionals need to get to. So here's our data overview. This is, yeah, I can't really turn this to light mode. I don't think this is just the GitHub page. So this is our class balance, but this is the normalized class balance right here. So our trained sample is like several thousand images. The test sample is like several hundred, and the validation sample is like literally 16 or 8. I think, yeah, 8. Or no, sorry, 16, right here. So, but for this graph right here, I normalized it just to show how the class balance is distributed here. So this data came from a women's and children's hospital in Guangzhou, China. It's very late and you need a sugar rush real quick. So that's important to note because pneumonia is significantly more prevalent in women and children than it is in men. I learned that when I was doing this project. I'm not an expert on pneumonia. So that combined with the fact that this data set was taken of if you're getting a chest x-ray scan, there's like already like a strong assumption that we know you're ill, and there's a strong assumption that the illness is something to do with your middle or lower respiratory tract, lungs, trachea, all that stuff. So the fact that these people are getting chest x-rays to begin with, combined with the fact that they're all women and children, makes this class balance, which is pretty skewed, make a lot of sense. Like about a quarter, maybe a third, is actually just normal or not showing signs of pneumonia at least, and the rest is they have pneumonia. The test sample is less skewed, but still kind of the same lean, and the validation sample is arbitrarily set to be 50-50. So I was asked a couple of times, like, did you do any like resampling or anything like that? And I didn't, because based on those things that I just explained, this class balance makes a lot of sense just based on like the data source, where it came from, who it's of, all that sort of stuff. This is probably pretty representative of like true life in that specific context. Now that's still like a little bit controversial. There's still an argument to be made that for the model's sake, and like training the model, you might still want things to be 50-50, so it has like an equal sort of like ability to learn. Like it's just as important that it can classify a 1 as it can classify a 0. But yeah, so anyway, I decided to not go with any resampling methods for that purpose. So this is just as the data comes. This is the class balance and it's not normalized. So the light blue is pneumonia, dark blue is normal, light green is pneumonia, dark green is normal. And you can't see it, but there's the red here. That little deal sticking out. I set that, when I was making this graph, I set that to like stick out a little bit because that was the only way that you could even like visually see it at all. So moving on. Oh yeah, the data originally comes from Mendeley data, but I sourced it from a post on Kaggle. I wonder if this link will. Yeah, it does. Yeah, it does. Okay. It actually goes directly to the data set page. Yeah, so this is the data set. These are all the same size and all that. Another thing that I didn't do was, you can like skew and rotate and do some things to the images just to kind of give the model like a slightly different perspective of the images. I didn't do all that. There's always like another thing that like I can do. But it's like there's only so much time in the day. I only have 3 weeks left to do this capstone project, which is kind of concerning. Um, so, and I've had a lot of job opportunities come up recently, and so at this point, I'm kind of content to do the minimum effective dose with Flatiron, just get the thing done, because I really need to focus on these other like job opportunities that have come up. Um, this office that I'm in right now being one of them. What am I doing? I'm just randomly scrolling. Okay. Yeah, so data preparation, I've kind of covered all that. I'll show you the code in a minute. Modeling methods. I've mentioned I use a convolutional neural network. Basically, I started with a very simple convolutional neural network with only one convolutional layer. And then I tried a lot of different stuff, and I would analyze the performance of the model primarily based on recall. That was like the main thing I was concerned with, like improving with this project. And yeah, so I ended up with a slightly more complex like network architecture, but not as complex as I kind of thought it would be originally. I thought this was going to get like way more like just stuff, but it didn't, which was like good for me. Some other things that I like experimented with was like the learning rate, like what gradient descent algorithm I used. I ended up going with Atom, a learning rate of like 0.002 or something like that. Regularization, I tried a few different like kernel weights. What was interesting was like I had like regularization and like I declared the kernel weight in like one layer, and it was like much smaller than like the very next layer. Like the kernel, there was still a kernel weight, but like slightly larger. That was interesting that it worked better like on a gradient, and it was the same thing with dropout regularization. I'd had like some random dropout, and I dropped out like a little bit more in like the second dropout layer than I did the first dropout layer. There was only 2. So that was kind of interesting. 19 million parameters. So ChatGPT dwarfs this model, but it's okay. My little laptop is doing its best. Excuse me. I've had this really dry cough lately. I don't know why. It's probably that pollution in Ohio. Just kidding. I'm in Texas. Yeah, so more about like the kind of different things I experimented with. The first like major thing besides the model architecture that I looked at was the training protocol. So I had it set initially so that the model only saw each data point or observation one time ever. Between all the batches and epochs and all that stuff, I had it set so that it only saw each image once. And mostly I just played with kind of like the batch size and what else? I lost my train of thought. Your epochs, duh. So yeah, like your batch size and your epochs, and kind of how many times it like laps back and forth through the layers before it goes to a new batch. Playing around with a lot of like those different types of things, and eventually I landed on, I believe it was about 15 epochs. Yeah. And that was still, so like I ended up doing 15 epochs where it still only sees each image once. I tried using like an early stoppage callback to see if maybe it helps if it sees some of the images more than once or all the images twice or whatever, and it didn't improve the model at all. What we're seeing here is recall. The dot is on the training data, and the line is on the test sample. Loss and accuracy. So really interesting thing with that I found with this project was So the recall really wanted to be perfect, like a 1.0, but the loss function was, or like the value, I guess I should say, was like just astronomical. Like I'm talking like values of like 70, 600, just like bizarre like loss function values. So the game throughout the whole like iterative process with this project was basically how do I reduce that loss function, get the loss function as close to 0 as possible while still keeping the recall close to 1. It wasn't hard to get the recall close to 1, but the thing is, like, if you have 1.0 recall and like 600 loss, like all that means is that you're just predicting everything as the target variable, and so you're capturing all of like the true positives, but you're also misclassifying all of the true negatives as false positives. Um, so yeah, that was really interesting. That was kind of counterintuitive at times, but we got the thing done. Normally like I find it's like the struggle is to make the model like more like get to your target like more consistently and efficiently, whatever, capture your target and label it correctly like more often. But that wasn't the problem as much as like getting it to not predict false positives as often. So that was fun. Network regularization. So I used L2 because I didn't want to just like totally delete any like parameters from the layers, because typo. Because I was gonna also experiment with dropout regularization, which does just totally like delete some nodes, so it didn't make all that much sense to use like L1 regularization. So I went with L2. The kernel weights for the regularization were applied in the dense layers, and there's only 2 of them, I believe. 1, 2. Yeah. So these 2 dense layers right here is where the L2 regularization was applied, and it was like 0.005 in the first dense layer and 0.05 in the second dense layer. I think I need to update this README a little bit. So anyway, this was our L2 regularization, and this was the dropout regularization. So the dropout regularization marginally so where it says dropout regularization here, this is L2 and dropout regularization. I should probably clarify that. But yeah, you can see that we got like pretty close. This is like I was actually stunned when I got this result after applying L2 regularization. But then I went ahead and applied dropout, and it just like trashed it at first. But then when I tried like dropping out on a gradient, then it like actually like improved it like not astronomically, but like significantly nonetheless. Like definitely like measurable. And also like, because I was like struggling with the whole like recall loss thing I was talking about a moment ago, the fact that I actually had some like floating point here instead of just complete 0 made me kind of believe in this like a little bit more, because if I'm just getting like just nothing here, I just like seemed kind of suspicious to me. So the fact that I actually got like a floating point here, even though no like what is this false negatives were actually predicted in the set, the fact that it calculated that, I don't know, maybe I'm connecting like false dots there or something, but the fact that it wasn't just like a perfect 0 like was a little less suspicious to me. But yeah, so interestingly enough, like it was predicting all of the like the cases of pneumonia like pretty much all the time, and then like a lot of the time it would also predict like normal cases as like pneumonia cases. So I was really trying this like upper left quadrant, like the game was really to like increase this number like as much as possible. And so you can see here that we went from 0.14 and 0.23. So true negatives, false negatives, false positives to 0.2 and 0.18. So when we went from just L2 regularization to adding dropout regularization, we actually like basically like the only difference. We predicted all the same cases as pneumonia correctly. The difference being that less of the normal cases were being misclassified as pneumonia. So we had less false positives, more true negatives. Man, like every time I talk about false negatives and true positives and blah blah blah, all that, it makes me feel like dyslexic or something. I gotta look at my hands and figure out which one's the left. So the optimization algorithm. I was reading through like the Keras docs. I used Keras library for this project. I couldn't find anything like describing like a default gradient descent algorithm for the like neural network class object that you use in Keras. So I don't know if there just isn't one or if there is one and it's just really hard to find like exactly what that is. But anyway, up until this point in the project, I had not specified what gradient descent algorithm to use. So at this point, I did that. I tested 3 different ones: stochastic gradient descent, adaptive momentum estimation, ATOM, and adaptive delta, ADA-delta. I ended up going with ATOM, and then the next thing was, so this is like the model's predictions on the top, and then like the test samples actual like class balance on the bottom here. And so you can see like stochastic gradient descent versus ATOM, and ADA-delta was like not even worth plotting on the graph. Like it just assumed everything was pneumonia, just everything. It was really bad. So yeah, I didn't even like play with the learning rate with ADA-delta, or like I just like threw that out. And ATOM wasn't awesome. Like there's still a lot of improvement to be made here, but it's a lot better than stochastic gradient descent. So I proceeded with ATOM, and then I tried a lot of different learning rates. And I believe like the default learning rate, ended up being, when I say default, it's like the, I think it was you use scikit-learn in Keras to do that. I'll have to go through the code. But yeah, when I think you use like a scikit-learn class object to apply like the ATOM, as like a parameter. Like you create that class object and then you pass that in as a parameter, like when you're calling your compile function for your model class object. So Keras and sklearn kind of working hand in hand there. Anyway, yeah, so the learning rate, I tried a lot of different ones. Turned out that the default learning rate, 0.001, was the ideal one. And you can see, if I can get them both on screen. Yeah, just barely. You can see that there was like a measurable improvement, which is weird because it's the default learning rate. But anyway, maybe I'm not remembering that correctly. Yeah, so again, we're getting a little bit of improvement with our confusion matrix. Not a ton, but yeah. So as I mentioned before, recall was the main thing that I was concerned with. Even though it turned out that getting the recall right was like really easy. And so mainly, like instead of improving recall, like most of my work was centered around improving or reducing the loss function. So to provide some context, so like how to go about that, I relied a lot on F1 score. F1 score just kind of sort of gave me a better idea like what exactly is going on, other than just simply we're getting a lot of false positives. So again, here's that same chart showing, I didn't explain this earlier. This is showing what the recall, the loss, and the accuracy is like at each epoch. So there's 15 epochs. You can see there's 15 dots on each one of these plots here. So this is how each one of these KPIs, key performance indicators, is changing like as the model trains over time. And also, this is saying like, I don't know why this is saying validation accuracy, and I guess I just changed it on these and not that one. I don't know, man. I always like think I'm like, all right, this project's done, it's perfect, and then I go back like a couple weeks later and look at it, and I'm like, so many typos. But anyway, yeah. So that says validation. So it should say test because this is plotting the model's performance on the test sample, not the validation sample. Anyway, so here's our predicted versus our true class balance for the test sample, and here's our confusion matrix for that as well. So this is like about half of our negative cases we're still predicting as positive, but it's still significantly better from the baseline. And this is the same visualizations for the validation data. Now remember, there's only 16 observations in the validation data. There's 8 pneumonia cases and 8 normal cases in the validation data. So the fact that it got this perfectly is a little suspicious to me. I would have liked to maybe have a slightly larger validation data set, but this validation data was not predicted on until the very end of the project. And I reran the prediction several times, and it spit this out every time. So maybe those particular pneumonia pictures were just really easy to predict, or those normal pictures were like more obviously like normal or something. I don't know. But congratulations to the little model. It got the validation data perfectly. So this is my conclusion. Reliability and limitations. Okay, so this is more interesting. Like I said, this data set was from one hospital, which is a women's and children's hospital in China. So there's like a few things we have to consider there. The lack of ethnic diversity. I'm sure there's like a wide variety of like Oriental ethnic groups in China, but that's still, we have to assume that there was like little to no African genetics, like Central or Northern Eastern European genetics, like Northern Asian, like, you know, like Russia, Mongolia, all that. Like Southeast Asian, like I already said African, like South American, North American, like we have to assume that like these people are basically all Chinese, and we know that they're all women and children, right? So the only male genetics in this data set are not even teenagers yet, I believe. So that means that if we took this model and then we tried to predict pneumonia on a bunch of chest x-ray scans from like a men's hospital, not that that exists, but like in North America, there's a good chance that we'd get like pretty much like 50-50, like random odds on like how often it's right and how often it's wrong. Maybe not that bad, but that's the assumption that I would make like going into that. Because I'm assuming that like has like an impact on what like the model's seeing and what's your man, how do I put this? So like your anatomy is definitely influenced by your genetics, right? And that's what the model is like looking at, is like what is like natural human anatomy in this image and what is like unusual and doesn't belong here, and then that's kind of how it's like figuring out like what's pneumonia and what's not. So that's problematic that every single observation in this data set is from a very like narrow scope of like genetic diversity and age range. So there's no like, well, I guess it's women and children's hospital, so you might have like elderly women in there, but there's no elderly men. There's no men in general. You know, that's I'm rambling. My point is that we need more data, and we need data from a like more diverse ethnic background, or pool, so to speak, right? So that's a major limitation of the model. My recommendation, if this were like for real, excuse me, moving forward would be to first begin with other women's and children's hospitals on other continents, right? And other like probably like 2 or 3 like on like a given continent. So like get like a couple in North America, a couple in South America, 2 or 3 in Africa because Africa is pretty large. Like get some. I was gonna say Southeast Asian, but I don't actually know where Guangzhou, China is. I went through this whole project, and I did not once Google Map Guangzhou, China. I hope I'm saying that right. But if I'm not, sue me. I don't speak Mandarin. This might be a good opportunity to work on my Google API skills. This video's gonna get taken down because I'm plugging Pepsi too much. Dongguan, yeah. Foshan, Zhaoqing. I wonder. I bet. Okay, so it's like right next to Hong Kong. I bet there's definitely like Chinese kids that get on Google Maps and look up like Texas. I'm from Texas, and they're like, Texas, yeah. Okay, so that's Southeast Asian. This little red line here, that's Guangzhou. So, yeah, this is still China. This is like significantly different geography. So I'm assuming that the kind of like ethnic profile or genetic profile of people from that area is going to differ. I mean, we're looking at like a whole continent here, especially like Mongolia and Russia. The data set from this area might like this population might be fairly similar to like kind of this like there's a name for this peninsula, I forget what it is, but kind of everything that the South China Sea touches, like maybe you could get away with, but much beyond that, the model I think is going to struggle to recognize like exactly what's going on. Yeah, this kind of, I guess you'd call this the Middle East, like getting some data from some hospitals there. Obviously, you would want like several from Africa because that's one of the like most ethnically diverse groups or areas, continents like in the world. I'd love to visit Africa one day. Europe, of course. Europe's pretty, you have some pretty distinct ethnic groups in Europe. North America would be interesting because North America is, at least by like ethnic groups and genetics. I hope I'm using the word ethnic correctly. I'm sure somebody will let me know if I'm not. Yeah, but anyway, there's so much like genetic diversity in the U.S., so that would be interesting to get a data set from the U.S., Central America, South America. South America is pretty diverse. You have these kind of more temperate climates down in the south and like more tropical climates up here. So like you would imagine that would create some genetic diversity as well. The island nations of like Oceania and all that. And then now we're back here in China. So yeah, my point being, if we took like, this data is all trained on like people from here, and then if we tried to use it on people like from here, or especially like people from like West Africa, it's gonna have some trouble, right? And so that's a major limitation of this model. But that said, the same kind of like training protocols and everything can be reused. We would just need to like retrain the model on an expanded data set is basically like what the punchline is there. That was like 10 minutes of me trying to say that, basically. Yeah, so negotiations or recommendations moving forward. Again, this is like kind of, you're like playing make believe that like you're actually doing this like for a business or whatever. Negotiate a partnership or a buy with an existing medical software provider. When I present the project, that's the instructor that's grading my presentation is like that person, the stakeholder. Beta test with select medical providers. So data set, all that thing aside, it'd be interesting to see how this tool actually like works in production. Like, you know, you're an x-ray technician, now you have a new feature, you got a little extra button you can click and you can use that tool now. How does that actually impact like timeliness and precision of diagnostics? Like, how does it actually affect like the workflow, right? Never mind like how good it is at actually like classifying pneumonia, but how does the tool, more so like not necessarily the model, but like the tool, the user interface, how does that impact the actual people using the tool, right? And like their ability to get work done in a timely manner. So that would be something that would need to be explored. Gather data even outside of beta testing network. So like the idea is that like when you beta test it with these like select offices, like all the images that they're using it on would be collected and then used to expand the data set, right? But also we want to make sure to go get those like, you know, Australian and West African and North Asian and like all these other different like data sets. Expand classification to include bacterial versus viral pneumonia, not varial. What's crazy is like so many instructors have like read through this whole thing supposedly, and none of them also have caught those typos. So, you know, your brain just kind of sees what it thinks it's like supposed to see, right? So anyway, expand classification set to include bacterial versus viral pneumonia. So right now it's just a binary classification, or we're predicting, you know, pneumonia or not. But if it's you know, like predict 0 or 1, but have like a 1.1 and a 1.2 or something, that wouldn't really be how you do it. But like a 1A and a 1B to indicate that it's bacterial or viral pneumonia. That would be something worth exploring. That would actually probably require some modifications to be made into like how the model is actually like structured and trained and like that sort of thing. And expand the model's ability to generalize on all of those things that I've mentioned, like basically would be doing that, expanding the model's ability to generalize unseen data. Can't tell you how many times I've said that sentence in the last, I don't know, 6 months. However long I've been doing this. Yeah. So we got our EDA, our modeling notebook, and a cool thing that I did for this project, for the sake of efficiency. So actually, let me start from the beginning here. So I made a Jupyter notebook, and I went in and I just kind of familiarized myself with the data set, got some of these plots made. So here's another example of how you just can't see the validation set. So, and here's how I'm like actually instantiating the data. So I created a few of these functions so I wouldn't have to rewrite all this code all the time to crank out. Like this actually returns like 4 different values. Returns like your recall and your loss, a classification report, so that's from scikit-learn, a confusion matrix, it's just 2D array in NumPy, and your y prediction, a vector of your predictions for y, and then a vector of your labels for your true labels for y. So I made this one function that like does all that for me. It was super nifty. This is all the stuff. So here's like your loss and your recall. Here's your classification report. And here's your confusion matrix. And I didn't print out the prediction label vectors. Anyway, this is the function where I'm visualizing the model training history. Also, as you can see, I added doc strings to these functions because I'm a responsible programmer. Yep, there's an example of that in action. And then here's the function that produces this like prediction to true label comparison. And here's the function that creates the confusion matrix. So I took all of that, I developed that in the EDA notebook, and if we look in the modeling notebook, I basically had 2 Jupyter notebooks, an EDA and a modeling. EDA for exploratory data analysis. We'll go through here, and I had to instantiate the data in the same way, of course. It didn't really make sense to write a whole function because I'm just going to do it once. Baseline model. Yeah, so I import my own little module that I wrote with all those functions that I just showed you. And then I call it here and get all those variables made. So every time I compile a model, I call this function, and then I get all these variables containing all this super useful information about the model. And then I can just call the function to do the thing for me. And what's so awesome is what I've done before is like I'll like up here in the top of the notebook, I'll write the function, you know, I'll do def and then like whatever. But now that's not even in this notebook, right? It's not cluttering up any of that. Like, it's just so readable. Yeah, so all I do is have to import. I called it Project Toolkit, so PTK seemed like a good alias for it. And yeah, I just import that library or module and call the function, and Bob's your uncle. Summary, yeah, and so every model that I compiled and fit, I used the PTK functions to analyze them, and that made the diagnostic like process like so much easier, right? So if you're curious about that, we'll go to projecttoolkit.py. I'm importing all my dependencies and everything here. And this is basically the same functions that you see in the EDA notebook. There's a few little, tweaks that I made. But yeah, that's it. Oh, and I even have this where I can print out, like, if I forget, like, what the name of a function is, I can just, like, print it out. The list of all the functions available. Probably not the best way to do that. I'm sure there's, like, better ways to solve that problem. But it's only 4 functions, and so, yeah. I'm probably, because my capstone project is also a convolutional neural network computer vision thing, and so I'm probably going to reuse this same module again in my next project. It'll be like another file. I'll just copy and paste this .py file to that directory. Yeah, dude, if you have functions that you need to reuse a lot, and you're dealing with like multiple different notebooks or even like different script files, like Py files or whatever, like do this. Just create your own little module. You got to be like kind of diligent about what directory it's in and everything, so you can import it directly. But just like figure that out, and then boom, like just I love myself so much for doing this for me. It was just so nice. Yeah. So, that, ladies and gentlemen, was my Phase 4 Milestone project at the Flatiron School. I hope you enjoyed this or got some value out of it. If you're curious, I will link excuse me. I will link this repository in the description below. If you're curious about Flatiron School, just Google Flatiron School and you can find out all about it. My capstone project is, like I said, it's a computer vision neural network thing, where it's going to look at pictures of coffee beans and predict, or classify rather, what stage of the roast process the coffee bean is in. So is it raw? Is it white? Is it light or dark roasted? And I'm a huge coffee guy. I love coffee. Make a mean cappuccino. So yeah, that's I'm super excited about that. Yeah, so that's it. That's it for the video. I might make like multiple of these sorts of videos for the capstone project. Also might not. Like I said, I don't have a lot of time. So yeah, anyway, I'll see you when I see you. Next time I see you, I'll have some cool coffee bean computer vision stuff going on. So yeah, till next time.